My name is Dan Jones. I am the first speaker today. My background is electric motor design. Revolution Motor is a relatively new R&D company. It has come up with the technology that I will present. As an R&D company, they're not looking to build the motors, they're looking to license what they have with motor companies of one kind or another. And as I go through the presentation, you will see that this is one way to move from one level of IE to another level of IE when I get into the various efficiency levels. And you do not change any parts except the winding. Well, the outline, I'm not going to read it. You can scan it faster than I can say it. But you'll see that energy is the focus. Here is a solution to getting better energy utilization. I will cover applications. I did put in the EU standards to give us a baseline comparison in terms of what we're doing. Certainly, AC motors dominate in the speed-based applications. Servos, step motors are a completely different segment of the market. That is the position market. So right away, we're making a differentiation. We're only going to talk about speed-based applications in terms of today. There's a lot of competition going on. When I looked at induction motors 15 years ago, I said, I don't know where we're going to go with them. They're pretty much frozen. Well, I was wrong. They're moving, and they're also getting lots of competition from other motor technologies. So I'm going to have to cover some of that as I go through the presentation. I then will get into RMI in terms of what they're doing and how they're doing it, because it is a patented technology. And then I'll give you some examples of things that have been done. You know, if you're working on induction motors and it's three-phase motors, you're going to have to cover a wide range of kilowatt outputs based on the standards that exist both in North America and here in Europe, in terms of where we're at. So I'm going to cover 3 examples. Now we're doing a lot more now because these examples are based on one unit. If you're an engineer, you know trying to base any technology on one unit could be a very dangerous thing. So I'll talk about some of the things we're going to be doing in the immediate future. Okay? Well, this is an obvious slide. It's telling us something we all should know. Energy is a very important thing. Why is it important? Why are motors involved in it? Well, quite frankly, electric motors use almost 50% of all the electricity around the world. So 50% of our power plants are driving just electric motors. Lighting is only 19%. So you know why the target to try to control the efficiency of an electric motor has become so important. It is the majority user of electric energy. Well, here's a slide I took from a colleague, you know, looking at motors cost too much to run. You know, in America, we have a nasty habit of buying on acquisition cost and not looking at the life cycle cost, which is something that's beginning to change. Europe has been much more sensitive to that than we have been on the other side of the pond in terms of where we're at. But if you look at this, you can see the running costs of a motor. It's the bar to the left is much more important than acquisition cost or installation cost. Roughly 3% of the total life cycle cost of an electric motor is in buying it. The other 97% is in using it. So that's part of our focus. Now you go all the way down to the right and we're into what in America we call cell phones. You have a different name here, and I'd love to tell you I remember it, but I don't. Well, what applications use these motors? Where do we find electric motors of the size that I'm talking about? From 0.75 kilowatt to 375 kilowatt, 3-phase types. Well, the major markets are compressors. Mechanical movements mean gears, pumps, and fans. And this is the North American. I couldn't find a European one, so I left this in. I'm sure they're pretty similar. Well, certainly AC induction motors are the most dominant motor technology in terms of consuming electricity. They run continuously for long periods of time and possess a measurable efficiency. A servo has no efficiency. It goes up and it goes down. Robot would be an example of that. So how do you measure efficiency if all you're doing is climbing up, climbing down? You have to measure energy, not efficiency under those rules. Well, there's a chart that I pulled out of the EU where we're talking about the various levels of efficiency that are presently being used or will be used here in Europe in terms of where we're at. We're looking at the right-hand side as being the European side, and I tend to love the IE designations. In America, we're sooner or later going to run out of nomenclatures. We're at premium. What are we going to be? Super efficiency and then ultimate efficiency? Well, there are companies working on IE6 and higher. And there is an interesting thing because IE4 is not official yet in Europe in terms of where we're at, but it's already in the standard and undergoing review by the various country engineering organizations in terms of where we're at. But that's not the stop for this. If we bring in new motor technologies, we can go much, much higher. And that's what's beginning to happen in the market. IE8 is not going to be a difficult thing to reach. The only problem is doing it for the proper cost. You know, that is our biggest problem. Obviously, permanent magnets come into play, and I'll get into that in a minute. So I'm going to be looking at the various levels as I talk about RMI. Well, for those of you that follow it, here's the directive, here's the things it covers. Again, I'm not going to read it. The presentation will be on the internet, so you'll be able to download it. So I'm going to move quickly to try to stay in time. And here's what's not covered. Now, Europe is a little bit different than the US. We've gone in the US to covering gear motors and motors with brakes up to a certain level of power. Europe is approximately 1 year behind us. Next month is when our next level of premium is official. But we've had that a premium for the last 4 years. It's not something new. Instead of going to a higher level of efficiency, we went horizontally into more motor types for the induction motor. Lots of different kinds of induction motors, three-phase type. In Europe, it's tracking fairly close to what the US is doing with its own local differences. Well, here is one of the better summaries I've found if you look at the various IE levels. You have, I call it the beginning, IE1, that was what originally was out. IE2, was the first major change to efficiency in induction motors. We're now moving to IE3. Now, as you look at the chart, you'll notice that the differential improvements in efficiencies get smaller and smaller as I go from IE1 to IE2 to IE3. The rules that are being used in the market is if you can reduce the losses inside the motor by 15 to 20%, you can claim a higher IE level. But it's not official yet. So we're all using it, but it's not a spec as yet, but it will be. Well, when I look at efficient motor types, I have my list, and it's reasonably long. I worked with a group that had a single-phase AC induction motor at 91% efficient. Up until that point, I thought 75 was a good number. So you can really do some real interesting things with design. Of course, the focus is on three-phase AC induction. And here are the competitors. The brushless PM, brushless DC, brushless permanent magnet AC. This particular motor type has a lot of names. Once a motor technology gets important, we have 3 or 4 different names for it. Everybody wants to claim a part of it based on its name, okay? And that's where the brushless PM is at this point. Synchronous reluctance, certainly ABB is a leader there in what is going on. Switched reluctance, we have Emerson doing some things there, Nidec Emerson. And then hybrid motors. There are some motors that use 2 motor technologies, an SR with a PM. I'm not going to cover them because I don't have time. That's a different presentation in the future. Well, everything goes around motor loss reduction. How can I get the watts inside the motor by changing materials, by doing a number of things, which I'll get into in a couple of minutes, okay? So this particular slide points to the various places where you can save efficiency. Materials play a big role in what goes on, and we have some new ones that we'll talk about. One of my favorite slides is the next one, and I apologize for the horsepower. This comes out of the US. We just haven't gotten to out of British Imperial yet. We're still using it. Well, you can see the breakdown of the losses inside a motor. There are 4 major parts. I squared R, the resistance of the winding, is usually number 1. A magnetic core loss, that's eddy current and hysteresis losses from the materials in the motor. Then we have our friction and windage losses. And then finally, the losses that I'm still trying to understand called stray losses. It's sort of a collector of those types of losses that we really don't completely know where they come from. Generally, they're from the end turns in any motor. But if I use a slotless, brushless, ironless configuration, my stray losses go to 0. Now, there are motors that are that out there. They're not in the speed market as yet, but you will see a couple in the near future. Well, how do I get lower losses? Here's my list of what you can do for these types of losses. A longer rotor and stator lengths. This has been done from IE1 through IE3. We're beginning to run out of the ability to just make the motor axially longer. So that one's starting to fade. Magnetic steel helps because the losses will go down. But now we have the role of cost that we have to worry about. Oh, we go on to, let's go thinner laminations. That'll help too with losses. But there's a cost impact. More copper certainly works. I'll put it in the rotor, cost, in terms of what we're doing. Synchronous motor types, well, that includes PM, synchronous, and switch reluctance. Let's switch. Now with the PM, we always worry about the magnet because it is the most single costliest element inside a PM motor, is the magnet, okay? But we've got the synchronous reluctance and switched reluctance motors that could get out there. Well, the synchronous reluctance has one limit. Its power factor goes to hell in a basket as you reduce the load on the motor. The switch reluctance motor, you must do the drive at the same time you do the motor. It is a matched pair in order to make it work properly. Well, the last one is the one I'm going to spend the time on. I'm going to look at the stator winds and try to figure out a way to increase efficiency just by taking the winding out of a motor and replacing it, or by doing it, you know, at the beginning of the process. Let's start to begin to look. So we've taken a walk through where the technology is, what very briefly is going on. Now let's look at one element of what Revolution Motor is doing. Well, I'm going to try to review as briefly as I can, because I only have 45 minutes, and I can certainly talk a lot longer than that. But I don't think the organizer would like that, so let me keep moving. We have the 1.5 kilowatt. We have a 37 kilowatt and a 225 kilowatt motor. All these have gone through the RMI conversion of the winding, okay? Starting, by the way, with the big one, the 225 kilowatt motor, which I'll get into a little later. And now, instead of doing one at a time, we have 5 3.7 kilowatt motors that we're going through because we need to learn more about tolerances, you know, and how do we tune it, because it does have to be tuned. But we're looking at going from IE3 to IE4, where the cost of doing it is no more than 7% of the total cost of the motor. So it's got some possibilities in terms of where we're at. And you don't need permanent magnets. And that's a heresy thing for me to say, because I've spent 45 years developing permanent magnet motors. Well, what I want to do is take an IE2 and move it to an IE3, take an IE3 and move it to an IE4 by just changing the winding and going with two windings, a main and an auxiliary. And in the auxiliary are smaller capacitors. I'll have to get into that, because I've always had some problems with capacitors. So this is the first time I've ever talked positive, I think, about them, in terms of all the times I've used them. And you get better performance across the wide range. Most of the standards call out at least 6 test load points, starting at 25% load all the way up to 125% load. So you're not looking for just one point, although all of us talk about 100% load as a peg point in terms of what goes on, okay? Well, I'm going to look a little further as we get into some of the data in terms of where it is. And I want lower starting and inrush current. I don't want to have problems when I turn the motor off with a jump up in voltage, which can happen. So I've got a number of things I have to check. The motor is a line start motor. You do not need a VFD, and that's one of the trends in the market. How do we get the efficiency up? Because an induction motor is very poor at 25 and 50% loads. It's horrible until you get up over 100 horsepower or 75 kilowatt in terms of where it's at. So we're going to look at some of the efficiencies at the lower levels, because very few motors operate at a constant speed. The name of the game is now variable speed. You either have to put a VFD with it, or you have to have an invention that can handle it directly in terms of where we're at. Now, I also want to improve power factor, because that goes terrible even faster than efficiency does at light loads, okay? 25% and 50%. Well, the key for RMI is breaking the winding into two parts. We have a main and auxiliary. We have to segment them into approximately 75 in the main, 25 in the auxiliary winding. We have to phase shift one winding with respect to another, because you're going to take some losses inside the motor and shift them to where they're positive, not negative. That's part of the a patent on the basic design. Now, the other thing, if I'm only driving 20% of any power, I don't need large capacitors. They're much, much smaller, and they're longer lifed because of that. Well, here's part of the trick if you're looking at a delta winding. You take the circulating current, shown in blue, and you shift it to where it's now positive instead of negative. So on the left, it's negative because it's working against the red. On the right, it's positive because it's in the valley of the red. So that's one of the invention. I hate to use the word tricks, it just doesn't sound right. That's one of the elements of the invention. Another element of the invention is if you have capacitors, generally when you turn them off, you'll get a voltage spike. Well, you don't get that with this based on the smaller size of the winding and the capacitors within the auxiliary winding, because that's where they go, not in the main, in terms of where they're at. So you get an immediate drop-off, and what the spikes tend to do is it wears out your insulation system. In some of these earlier inventions, it could go up as much as 40% when you disengaged the induction motor using a two-winding approach. Well, my challenge, improve both motor efficiency and power factor over a wide range of levels for 0.75 to 375 kilowatts, okay? Operate successfully in both Y and delta. Now, there's something else going on. The Y does not have circulating currents inside the delta winding as it does. So we're having something going on with the magnetization current for the Weiss. I'm in an interesting situation. In theory, we're not quite sure how it works, but I've got all kinds of test data from nationally recognized test labs to tell you it does. And I'll get into some of those details shortly. You know, and the added value of the auxiliary capacitor allows me to tune it better. There is a formula in the patent that gets me within 10 to 15% of what the capacitor should be in the auxiliary winding. And from there, I cut and paste, I guess would be the term I might use. You know, I've got to change it to see if I can peak everything. One other thing we learned is if I get the maximum efficiency, I'm not at the best power factor. But since the improvements are more pronounced with the power factor, I can always bias it toward getting the best efficiency. Induction motors have very poor power factor at light loads, unless they have a VFD. That's part of the reason for looking at the variable frequency drive. Well, here's the small guy. This is a 1.5 kilowatt. It's under test. It's tested by a company called Magtrol, which is one of our major suppliers of test equipment for motors in Buffalo, New York. There's some of the data. In this particular sheet, we were trying to find what the best position was. So what are we varying? We're varying voltage. We're varying capacitance. We're looking for that sweet spot, okay? Once we find out if it's at 414 volts, all I have to do is change the winding to get back to 460, which is pretty straightforward. But I got to find that sweet spot first. Well, here's the summary of the data in terms of looking at a standard motor. This, I believe, is an IE1, and we were looking at going to an IE2 to see if it worked at that level. And it did. You can see the standards versus the RMI, left column, right column, and then the power factor, significant improvement. So we got good improvement on the 1.5 kilowatt. Well, let's go up. Let's go to a 37 kilowatt. Again, my American background comes in and I have to talk horsepower. I apologize for that. What's 37.3 kilowatt? Now this is tested by the national recognized test lab called Advanced Energy. They're the #1 test facility for Department of Energy in the US. So this is a golden test for us in America. If they say it's better, it's better. There's no argument with them based on the reputation that they have in the marketplace. Well, that's the beginning sheet. I believe we took a Baldor motor, cut out the one, tested it before we cut out the winding, and then retested it. So that was the process. Well, here's before the conversion, the measurements. And I have a better slide. I wanted you to see the actual data sheets from Advanced Energy. To try to read that is a challenge. But again, it will be on the internet, so you'll be able to get it there, okay? But I have a simpler chart in two. Here's with the conversion. If you looked at the white circles, that's your power factor. It's almost at unity. The efficiency peaks at about 75%, which in America is where we seem to want it to peak. I don't know why they don't let it peak at 100. As a permanent magnet guy, I wanted to do it at 100, not 75. But I'm not going to win an argument with my compatriots. Well, here's a better summary for it. In terms of efficiency versus 25, 50, 75, and 100% load. I left out the 115 and the 125, but in the original data sheets, they're there. Well, at 50, you know, you've got a pretty good motor efficiency without RMI, but it still moves up from an IE2 to an IE3 level at 100%. And it's better at all the others. But look at the power factor. Look how much better it is. And the combination of the two add up to the current I'm going to draw out of the power to the motor. So I want both. I don't want just one. In America, we don't pay much attention to power factor. But in Europe, they certainly do. Okay? Well, the last one was really the first one that the technology was looked at. This was a motor that was used in a mine for circulating water for cooling. It was a coal mine, so at this point, because of the way we're handling regulations on coal, it's not operating anymore. But it operated for 12 years before it was shut down. So we took the old motor. This is the test vehicle, the initial one. We had to cut the windings out 5 times in order to get the balance that we wanted. And that's using FEA to help us. Well, if you have long leads, and there was a 100-foot lead on this particular motor, you get a much better improvement when you have long leads. You know, the leads, when you're drawing a lot of current, become antennas. They become their own load factors, you know, with what's going on. Again, the chart. Well, we saved 69,000 kilowatts at this big motor. This is the original data. Again, I'm not going to try to read it. I'm going to take you, it's there if you want to look at it. This is my summary. Now, the original IE2 equivalent in America did not, at 300 horsepower, was not touched. Our original EPAC laws only went up to 200 horsepower. Now everything is up at premium efficiency level. So that's the reason why I don't have the answers for 25, 50, and 75 on efficiency. I did have them on power factor. So here we are. Again, you'll see we did a great job of tuning this for power factor. We did a reasonable job for tuning it. But one of the things that, and by the way, the standard for IE4 will be 96%, so we just missed it. For all the others, we exceeded what the standards were, based on the earlier chart from the EU. This, we didn't quite make it. Well, in 300 horsepower, we started with FEA sims. We had to look at the power factor and the efficiency, so the curve is there comparing them. Now, I'm not sure if this is a Baldor. The other motors for the smaller sizes, we started with Baldor, which is the leader in the US in terms of sales. We met the torque, which is one of the things one has to do. One of the problems is starting a motor, even a 3-phase motor, doesn't start as easily as you like. This is looking at the first 10 or 15 milliseconds of the starting of the big motor, okay? That's your scale you have at the bottom. And, in looking at it, RMI had a much smaller variation than the original Baldor motor. We're looking at inrush current, because that can be a bear with induction motors. In terms of that, well, it's 15% lower than the original motor before the change. All right. So if I try to summarize, and by the way, I've taken you through pretty fast. If I try to summarize, here it is, 3-phase motor, main and auxiliary. In this case, delta, but Y also works, okay? We have to offset the winding by 90 electrical degrees between main and auxiliary. This is all in the patent, which is why we can talk about it. Main winding is 75% of the motor power, and we reference it by power. Auxiliary windings are installed at the bottom of the slot for the stator, okay? Because if you put it at the top and the bottom, you have different leakage currents, so you have to keep things pretty consistent. The auxiliary windings have a capacitor in series with the winding, with the auxiliary winding. Since it only has 25% of the power, some cases a little less. It can go all the way down to 20%. The capacitors we use are much smaller. Smaller capacitors are certainly a lot safer than the big ones. I don't even remember what the 300 horsepower was, but we were talking over 150 microfarads, 200 microfarads for the big guy. And we figured out a way to distribute it to make it easier. Okay. Cabling can be a problem, so you have to worry about that. It's not just the motor. The cabling adds losses. So you have to consider that in what goes on. And the capacitor value is calculated from a series of formulas in the patent. RMI has achieved their objectives of improved efficiency and power factor levels across a wide range of power levels and loads. Only the winding has been changed, and smaller capacitors have been added. 3-phase, 3 capacitors. Intensive testing by third party. We're getting ready to test the 5 3.7 kilowatt motors and see what kinds of variations we get. Now we're into tolerances. The first set through was concept. We're finished with that. Now we need to learn a lot more. Well, we took a premium efficiency in IE3. What we hope to get is an IE4 using this technology. More FE simulation work will help us. We have to understand why it works. We've measured it. I can remember an IEEE guy, and I've been a member of the IEEE for decades, saying, well, you don't know how it works. And my comment was, all I know is it does work. That's a lot better than theory, the actuality of what's happening, okay? We are an R&D company. We're looking for licensees. This is not a motor company. Somebody came up with a good idea. I'd love to claim it, but it wasn't me. Now, this is just the beginning of saying, where is the market? Because what's happening is in America, we're only rated to IE3. Europe today is also going to IE3. Well, the market's gone well beyond it. So we're away from a regulation scenario into a market scenario. Why? Because each one is looking for a unique feature to make it better than their competition. Novatorque is the leader. I finally got to WEG. WEG is 95.3%. I want to get some other data. If somebody has some data sheets they'd like to give me on IE4, IE5, I'd be happy to take them. Because this gives me a thumbnail sketch of where the market is in the US and in Europe in terms of where I'm at. Well, I'm finished, and it's now time for you to decide what you want to ask me. Thank you.